Single photon averaging diodes, or SPADs, are an emerging sensor technology capable of detecting individual photons and recording their arrival times with high timing precision. Due to these abilities, SPADs are now used for a wide range of active transient imaging applications, including LiDAR, fluorescence microscopy, imaging scattering media, and non-line-of-sight imaging. Our goal is to leverage SPADs for passive photography, especially in scenarios involving fast camera or scene motion, which is common in both consumer and scientific photography. We take inspiration from conventional burst photography and propose Quanta burst photography, a computational photography technique designed for high-speed binary image sequences captured by a SPAD camera. The binary images are aligned and merged to generate a high-quality image with low motion blur, low noise, and high dynamic range. Please see the paper for algorithm details. Next, we show some results generated using a recently developed SPAD array, which captures binary images at close to 100,000 frames per second. Here is an example binary image sequence captured by a handheld SPAD camera. Each individual image is quantized to 1 bit and extremely noisy due to the randomness in photon arrivals. This is the image generated by averaging the sequence of binary images. Since the interframe motion is not compensated, this image has large motion blur. This image is shown only to demonstrate the amount of camera motion and is not meant to be a comparison. By using the proposed techniques, the binary frames are aligned and merged to create an image with low motion blur. This is the same scene captured under extremely low light, with the SPAD camera being handheld. Each pixel, on an average, receives only about 50 photons over the entire sequence. Due to the sparsity of photon detections in binary images, it is almost impossible to recognize the scene, making it challenging to estimate motion. Quanta burst photography is still able to generate a reasonable image. In such extreme conditions, a conventional camera would capture images with either heavy motion blur or strong noise. Although it may appear that SPADs are useful only in low light conditions, due to their image formation model, they can also image bright scenes where conventional sensors would normally saturate. Please see the paper for details. Here, we showed an example of the SPAD camera capturing a scene with high dynamic range. The camera is directly looking at the halogen light filament, as well as the text on the plaque, which is only receiving indirect light. The proposed method can be used to reconstruct a video by shifting the reference frame in time. The non-rigid motion of the strings is correctly reconstructed. In summary, SPAD sensors have the benefit of extreme sensitivity to light, high temporal resolution, and high dynamic range. Compared to current scientific low-light cameras, SPADs also have the benefit that they can operate in room temperature. Since SPADs are compatible with CMOS fabrication, they can potentially be manufactured at relatively low costs. With the ongoing development of SPAD arrays, we envision quanta burst photography finding applications in both consumer and scientific photography.